Whether in classical computing or quantum computing, 2-qubit gates are undoubtedly the most important bridge for establishing connections between qubits. Unlike classical computing, where logic gates such as AND, OR, and NOT gates and their combinations are used, quantum logic gates require all logical operations to be unitary transformations, so the number of input and output qubits is equal. A qubit is a unit of quantum information that can exist in two states, usually denoted as 0 and 1. However, unlike classical bits, qubits can also exist in a superposition of these two states, meaning they can be both 0 and 1 at the same time. Once you've established that background, you can move on to the specific topic of a 2-qubit system and its computational basis. A 2-qubit system can be described by 4 computational bases, each of which corresponds to a different possible state of the 2 qubits. These 4 bases are typically denoted as ket00, ket01, ket10, and ket11, where the first qubit is represented by the digit on the left and the second qubit is represented by the digit on the right. For example, the state ket01 represents a system where the first qubit is in the 0 state and the second qubit is in the 1 state. Similarly, the state ket10 represents a system where the first qubit is in the 1 state and the second qubit is in the 0 state. These 4 bases can be used to represent any 2-qubit state, and they form a complete orthonormal basis for the 2-qubit Hilbert space. In this tutorial series, we define that in the ground state ket00, the left 0 corresponds to the high bit, and the right 0 corresponds to the low bit. If the quantum state of ket00 is transformed into ket50, the quantum state of ket01 is transformed into ket51, the quantum state of ket10 is transformed into phi2, and the quantum state of ket11 is transformed into phi3, then we have the expression for the U transformation. Multiplying both sides by the transpose conjugate of the 4 basic states, and then adding the equations together will yield the general formula for a 2-qubit logic gate. Let's summarize the calculation process for a 2-qubit logic gate. First, we need to list the transformation table of all the basis states. Then, we use the general formula for the 2-qubit unitary transformation matrix to perform the calculation. Simply put, it is to right multiply the dual vector of each original quantum state by the transformed quantum state, and then add the results together.